We're going to introduce definite integrals today. We've talked about indefinite integrals before, which are just antiderivatives, where you make an integral sign without limits of integration, and all we're after is the most general antiderivative of the given function. Definite integrals are different. Notationally, they're different because we put numbers above and below the integral sign, but also what they represent is different, seemingly, at least at first. Seemingly, they don't represent antiderivatives, they represent areas under curves. However, the amazing thing, exemplified by the fundamental theorem of calculus, is that finding antiderivatives and finding areas under curves are actually the exact same problem, even though they seem different. That's the fundamental theorem of calculus. That's the most important theorem in calculus, is that realization. And you could even say that's the birth of calculus that Newton and Leibniz really discovered. People had figured out how to find areas a couple thousand years ago, at least of circles and stuff like that. And they even knew how to find slopes of tangents before Newton and Leibniz came along. But realizing there's a connection between the two, between differentiation and anti-differentiation, and finding areas under curves, that was really the birth of calculus. We can start this with a really simple equation. Distance equals rate times time. You might say, this would be, it's an exaggeration, but it's not too much of an exaggeration. You might say all of integral calculus is a generalization of this one simple equation. What? Are you kidding me? No, I'm not. It's not too much of a stretch to say all of definite integrals calculus is a generalization of this equation to, yes, more complicated situations. So it's not clear what the connection is all the time. But basically, this is the idea at its heart. Distance, like, okay, well, say you know your rate in meters per second. Maybe you're going 5 meters per second, and you know your time elapsed, say 10 seconds. Multiplying these two numbers and canceling the seconds gives you the distance traveled, 50 meters. It's very important to realize that you can interpret this calculation that we did here graphically. Graphs are important for derivatives. They're also very important for integrals. What we want to do is we want to really graph the rate as a function of time. And if I say the rate is 5 meters per second, well, I'm trying to hint at the fact that it's a constant rate. You're walking at a constant rate, or in this case, probably to go 5 meters per second, you got to jog at a constant rate of 5 meters per second. The graph of the rate versus time is a horizontal line, a constant function. Yes, this is a number, but I also want to think of it as representing a constant function whose constant value is 5 meters per second. And I'm graphing it over the time interval from, say, time 0 to time 10 seconds. And then this product, 5 meters per second times 10 seconds, is really the area under this graph over this interval from 0 to 10. Now, the units of this area are meters. And you say, wait a minute, how can area have units of meters? Wouldn't it be meters squared? Yes, the literal drawing, if you were measuring distances in meters, would have an area equal to something in meters squared. However, as far as the interpretation with the application goes, we think of time as being in seconds and the rate as being in meters per second. And we think of the units for the areas as being units for the vertical axis times the units of the horizontal axis. The units would be meters per second times seconds. Yes, I'm using inconsistent notation here, but it's hopefully not a big deal. The units for that area are meters for the application. It's all in terms of how you're interpreting the graph in the application. I'm imagining jogging at a constant rate of 5 meters per second for 10 seconds. I multiply to get my distance traveled to 50 meters. Just like to find the area of this rectangle, I multiply base times height, 10 times 5 to get 50. The units are units of this axis times units of this axis. Meters per second times seconds gives you meters. That's the units for the application. That's very important that you realize that you want to think that way in terms of understanding what integrals are for. So that's the most basic kind of application. We do want to work toward, again, generalizing this. Here's one way you could think about generalizing it. If you think of y as a variable representing distance traveled, think of v of t as being a function representing, oh, should I say velocity or should I say speed? At first, even though it's a v, I'm going to say speed. Speed at time t. It might be good to also add the word instantaneous in there. Instantaneous speed at time t. If you're driving your car, it's whatever your speedometer says at a given moment in time. Of course, it's all digital now. I'm still used to thinking of an analog speedometer sometimes. We used to have needles that go up and down for our speedometers. In the past, this could be a constant. This could be a constant function. If you're traveling at a constant speed, it would be a constant function. It would be a function whose graph could look like this, for example. But it could be not a constant function. It could go up and down like a sine wave, or maybe it just always goes up, you're speeding up, or maybe it always goes down, you're slowing down. It could be any function of time that is not negative. At least we don't want to think about negative speeds. We do want to allow for negative velocities because velocity is different than speed. I'll remind you of those differences. And we could also use, say, delta t, right? Delta times delta of a variable is a common notation for change in the variable. You could call this change in time. You could also call it time elapsed. With this notation, we could write y, well, if it was a constant speed, we could say equals v of t times delta t. But okay, maybe I also want to do something else. Let me do something else. Instead of I'm dealing with the total distance traveled, I'm also going to deal with delta y as being a symbol for the small distance traveled over a small amount of time. The delta t here is ultimately going to represent typically a small amount of time. Let me call it change in position. Well, or I'll call it change in distance here initially. Change in distance. Okay, I'm going to take these things and combine them. This is supposed to be a kind of a crazy looking arrow here. Into one equation, delta y, and I'm going to write it as an approximate equation, is approximately v of t times delta t. This, again, is just sort of an arrow here. I'm combining all these things. Yes, it's a weird looking arrow. This is saying distance is approximately rate times time, but I'm writing it as an approximate equation to acknowledge the fact that the speed may not be constant. Maybe you're speeding up, you're hitting the accelerator, or you're slowing down, you're hitting the brakes, or if you're jogging, you start running faster, or you slow down into a walk. The speed is not necessarily constant. If it is constant, then this is an exact equation. If it's not constant, it's an approximate equation, and the approximation is typically only very good if the time elapsed is small. Intuitively, typically, you might say, the approximation is quote unquote good, whatever that means, if delta t is quote unquote small. You know, good and small are not precise terms in math. They're vague terms, so that's why I have quotes around them. Okay? This approximate equation becomes the basis for approximate integration. Let's do an example. Well, let's do an example that's not constant, but is still linear, just to still keep things simple. V of t is, let's say, 2t plus 1. So this is my speed in, say, meters per second at time t. If you graph it, the graph looks like that. At t equals 0, it's 1. So whatever the first moment in time is that I start my stopwatch or my whatever you're doing to start the timer, at that moment, there is motion already. Motion to the right, say, at 1 meter per second. The fact that the graph goes upwards means you're speeding up. You're going faster and faster. In fact, your acceleration is constant. What would the acceleration be here? It's the slope. That's the acceleration in this context. And it's a constant slope of 2, the derivative of this. This is one direction of motion, to the right, say. In that case, the speed and the velocity are the same thing. The derivative of velocity is always what we call the acceleration. But again, here, because the speed and the velocity are the same because you're moving in one direction, the derivative of the speed is also the acceleration. Units for that would be meters per second per second. Shorthand for that is meters per second squared. That's a derivative, but we're after the total distance traveled. Before I think about it this way, let's reason out the total distance traveled a different way. I do need a time interval here, I guess. Let's go from t equals 0 to 10 again. I'm letting time go from 0 to 10 seconds, and I'm wondering how far do I go? I hope it makes some intuitive sense that since the acceleration is uniform, it's constant, this graph is a straight line, that my average speed should be halfway between my lowest speed and my highest speed. Does that make intuitive sense? My lowest speed is 1 meter per second. Plug in t equals 0 into that equation. My highest speed, if I plug in t equals 10, would be 21 meters per second. Halfway between those, this is not to scale, halfway between those would be 11 meters per second. 21 plus 1 over 2, that would be halfway between. So it should seem reasonable, this is no proof, but it should seem reasonable that my total distance traveled should not just be approximately equal, but should be exactly equal to 11 times 10. 11 meters per second times 10 seconds. The seconds cancel, giving you 110 meters. That should seem reasonable. That is an area of a rectangle. It's the area of this rectangle right here. Again, 11 is my average speed. Ten is my time elapsed. That's my delta t. That product is the same as the area of this blue shaded rectangle. And it is also the same as the area under the curve. That'll shade in red. Or it should be at least. Do you believe me? That area in red is the area of a trapezoid. The shape that's colored red is called a trapezoid. Let's see if the area of the trapezoid is the same. Trapezoid, I'm spelling it wrong. Well, what's the formula for the area of a trapezoid? It's the base, excuse me, times the average of the height, of the heights. There are two heights, 1 and 21. You do the exact same calculation here. There's the average of the heights. Is there another way to figure it out without doing the exact same calculation? We could break the trapezoid up into pieces, one piece being a rectangle and another piece being a triangle. Let's see if we do that, if we get the same answer. For the rectangle right down here, base is 10, height is 1, 10 times 1. For the triangle, of course, the area of a triangle is 1/2 base times height. 1/2 base is still 10 right there. Height now is not 21, it's 20. Right? The height of that triangle. 21 minus 1, 20. 1/2 base times height. Simplify, you get 10 plus 10 times 20 is 200, times 1/2 is 100. 10 plus 100 is 110. We get the exact same answer as before, 110 meters. The area of this blue rectangle, which is the area whose base is the same base as the interval of time and whose height is the average height, equals the area under the speed curve, the area of this trapezoid. They both give you the total distance traveled. It's not a proof of that fact, but it should make intuitive sense. It gets harder now, though, if the speed is nonlinear. Let's level up the difficulty level by 1 notch. What if v of t is nonlinear? Oh, let's make it be, how about t squared? This is an instantaneous speed at any moment in time. This function is telling you your speed at that moment in time. For example, if t equals 3, plug in t equals 3, you get 3 squared is 9. 9 meters per second would be your speed at that moment in time. Instantaneous speed. It's really a derivative of a distance traveled. Yeah, already there's a connection between derivatives and integrals really here. If you could, do phones keep track of speeds as you walk? Yeah, maybe not instantaneously. Or your Fitbit will, or something, your watch. Okay, so if you could somehow have a super accurate speed monitor, and this was your speed as a function of time, at time 3, you'd be going 9 meters per second. At time 4, you'd be going 16 meters per second. You're really accelerating quite rapidly, actually. Okay, you're quickly going to get to the point where you can't run that fast. The derivative of this is the acceleration because it's still one-dimensional motion. You could call it a of t. V prime of t is 2t meters per second squared. It's no longer a constant acceleration. It's an acceleration that is increasing. Not only is your speed increasing, but your acceleration is increasing. Not only are you going faster and faster, you're going faster and faster at a faster and faster rate. Hard to imagine. We're after, though, the distance traveled. Let's say this is our graph of v of t, function of t. Let's still go up to 10 seconds. Okay, this, by the time you hit t equals 10, you'd be going too fast. You can't run that fast. At time 10 seconds, you'd be going 100 meters per second, effectively running the length of a football field in 1 second. This is more like an airplane. Maybe an airplane can't even accelerate that fast. Once it's in the air, yeah, it can go like over a football field in 1 second. But when it's accelerating down the runway, even to take off, it's probably not going quite that fast yet, I think. I might be wrong. So what's the distance traveled, pretending you could travel with this speed as a function of time? It would still be the area under the curve. Now we could try to eyeball that area. We could say, hey, it's certainly less than 10 times 100, right? The area of this rectangle here would be 10 times 100, 1,000 meters. We certainly haven't gone 1,000 meters. It's also less than the area under this triangle here, right? It's below that triangle. What's the area of that triangle? 1/2 base times height. 1/2 times 10 times 100 is 500 meters. The area under the curve is less than 500. So even just a real basic approach like that would tell us the answer has got to be less than 500 meters, maybe in the ballpark of 400 meters, if I had to hazard a wild guess. 300, 400, something like that is a guess. It could be, I could be far off, but based on this possibly somewhat inaccurate picture. How could you figure it out more precisely? That's where it gets hard. Okay, so we're about to do harder things here. Our interval is from 0 to 10. I'm about to use some notation that's going to get confusing. That doesn't start confusing. I use the letter A for my left endpoint, as always. Use the letter B for my right endpoint, as always. And I am going to let delta t, let's put it over here, be, you might say, a small amount of time. But I'm going to not just write it down as a symbol, but actually come up with a formula for it. And the formula for it is going to be b minus a over n, which is the length of the time interval, divided by n. Well, what's n? N is going to be the number of approximating rectangles. Number of approximating rectangles. Well, what's an approximating rectangle? Well, one approximating rectangle is the entire big rectangle here, but that's not a very good approximating rectangle. I want better ones. I want to break up this interval into a bunch of pieces. Here I've broken it into 1, 2, 3, 4, 5 pieces, each of length delta t. In this case, if I've broken the interval into 5 pieces, delta t is going to be 2, right? 10 minus 0 over 5 is 10 over 5 is 2. 2-second time intervals. Is that small enough? It's not terrible, but we can do better. We could do delta t as 1, or delta t is 0.1 or 0.01 for more accuracy. But if we use a smaller delta t, we have to pay a price. N's got to be larger. We can have more rectangles. How should I make my rectangles? There's freedom. Not complete freedom, but some freedom. Just like to be a citizen in a free country, right? You have some freedoms, but not freedom to do anything. You don't have freedom to murder somebody. Okay, if you do, you'll be put in jail. You got some freedoms, but it's constrained. Here we have freedom in choosing how we make our rectangles, but it's constrained. Here's one way to do it. For each one of these little sub-intervals of the bigger interval, go to the right endpoint, and at that right endpoint, go up to the curve and then over, making a rectangle. Next subinterval, go up to the curve, go over, not all the way over to the horizontal, the vertical axis there, but over to the previous value of t right there. Make a bunch of rectangles like this, including with the last interval, go up like this. Those rectangles have a total area, you can see, is bigger than the total area under the blue curve. But if I add up those areas, it shouldn't be too far off from the total area under the curve. Certainly better than 10 times 100. Certainly even better probably than the area of the triangle, 1/2 times 10 times 100. Let's go ahead and figure out what that area is. Total area of approximating rectangles here in this picture in each case, it's base times height. In each case, the base is 2. What's the height? I hope it's clear you need the function to figure out the height, because that's how I made the rectangles. The first rectangle, to figure out its height, I have to go to time 2. There's a little 2 there. I'm just drawing it right now. A little 2 right there. I have to go to time 2 and plug 2 into the function. Multiply times the base. I'll call it delta t, but delta t is 2. Then go to the next moment in time, 4, for the next rectangle, the right end point of the next rectangle. Plug that into the function times delta t. Then on to the next one. And the next one. And the last one. Hey, that's not too bad to do. V of 2 is 2 squared is 4. Delta t is 2. V of 4 is 4 squared is 16. Delta t is 2. V of 6 is 6 squared, 36. Delta t is 2. V of 8 is 8 squared is 64. Delta t is 2. V of 10 is 10 squared, which is 100. Delta t is 2. It would be a little quicker to factor the delta t out and just add up the v values and then multiply by delta t. That would be a little quicker. But this does emphasize doing it this way, that I'm adding in the area of 5 rectangles, because each one of these is a base times a height. In each case, the base is 2, and the height is 4, then 16, then 36, then 64, then 100. So this becomes 8 plus 32 plus 72 plus 128 plus 200. See if I can do that in my head. That's 40. This is what? 200? 440? I didn't make a mistake. Look good to people. 440 meters would be the answer that we get as the total area of the approximating rectangles. It's an approximation to the area under the blue curve. Therefore, it's an approximation to the total distance traveled. Probably a little bit too big. Yeah, definitely a little bit too big, because these rectangles are above the curve. Add up all those areas, it's going to be more than the area under the curve. It's going to be what you could call an upper sum. Upper sum meaning too big. Upper, too big. You could also call it an overestimate, i.e. overestimate. It's got yet another name that's related to the fact that in each subinterval, I was using the right endpoint to figure out the height of the rectangle. Because of that, it's also called a right-hand sum. In this case, it's a right-hand sum. Right-hand sums are found by taking each subinterval, going to the right endpoint, and using that to go up to the curve to find the approximating rectangle. With a function, a speed function that's increasing like this, the right-hand sums will also be upper sums, over estimates. However, if the speed curve were decreasing, if you were slowing down, then the right-hand sum would be too small. The rectangles would be below the curve. If I drew a decreasing curve and did right-hand sums, rectangles determined by the right endpoints, they'd be under the curve. So right-hand sums just tell you how to figure out the heights of the rectangles. They don't tell you whether the estimate is too big or too small. Unless you happen to know the function's increasing, then in this case, you know it's going to be too big. If there's an upper sum that's an overestimate, is there a lower sum that's an underestimate? Lower sum, that'll be an underestimate. Will, in this case, what I'm about to write will be a left-hand sum. If there's a right-hand sum, there's got to be a left-hand sum. What's the difference? For left-hand sum, for each subinterval, use the left endpoint to determine the height. And in fact, in this example, it's a little weird, but with the very first subinterval, the left endpoint 0, v of 0 is 0. The speed at time 0 is 0. A little weird to think about, but true. We're starting from rest here and speeding up. And so there's really no rectangle at time 0. The first rectangle has a height of 0. The next rectangle would have a height v of 2. The next one, v of 4. The next one, v of 6. The next one, v of 8. These red lines that I'm just making right now are going to be tops of rectangles for left-hand sums. And you can see they're under the curve. The total area of all of them is going to be too small when the curve is increasing like this. As a sum, this is going to be v of 0 times delta t plus v of 2 times delta t plus v of 4 times delta t plus v of 6 times delta t plus v of 8 times delta t, and that's going to be the last term. Why is v of 8 times delta t the last term? Because this last subinterval goes from 8 to 10. The left endpoint is 8. You would use that to determine the height of this last rectangle, whose top is right there. Every term here, except for the first term, we've already had up here. But we do not include the very last term that we had up here. This is going to be, well, v of 0 is 0. 0 plus 8 plus 32 plus 72 plus 128. Exact same thing that I got up here for the first 4 terms up here become the last 4 terms down there. The 200 goes away, and there's a 0 there. It's worth writing the 0 because in general, it might not be 0. In this example, it is. And what does this end up equaling? It looks like 240 meters. Pretty wide spread in these approximations between 240 and 440. Right? That's not very precise. How could we make it more precise? There's a couple things you could do. You could use a smaller value of delta t. which means more rectangles, which means more work. Ugh. If you make delta t 1 instead of 2, you're going to have 10 rectangles instead of 5, 10 things to add instead of 5 things to add. In general, it would take twice as long. If you make delta t 0.1, answer your question in a second here, make it 0.1, 20 times smaller, or no, 10 times smaller than 2. Oh, sorry, got mixed up. 20 times smaller than 2. You're going to have 20 times more terms. 20 times 5, you'll have 100 things to add. A lot more work. 20 times more work. Of course, you could program a computer to do it for you. What's your question? Same delta t, is that what you're asking? They do not have to be, but that's the simplest thing to do. They can be different delta t's. The next, well, another way you could do this is less work. You could average these two numbers. When you average the left and right-hand sums, it's called a trapezoid sum. Trapezoid sum can be interpreted as the average of the left-hand sum, which I'll just abbreviate LHS, and right-hand sum RHS. Now, when you compute an average, there is a sum on the top, right? You add some numbers. But we're only going to add 2 numbers here. So why should we really call it a trapezoid sum? It's not like we're adding 5 numbers like we did before. The answer is because you can think of it as a sum like before, a sum of a bunch of trapezoids instead of a bunch of rectangles. But the quickest way to find it, if you've already done the left and right-hand sums, is just to average them. So the left-hand sum was this one, that was 240. The right-hand sum was the 440. Divide by 2. You're going to be halfway between those. It'll be 340. You can also compute that as 680 divided by 2, 340 meters. Is that right? Is that the distance traveled? No. But it's a lot better. It's a lot better approximation. What is the distance traveled? If none of these is right, what is it? It's the area under the curve. But what's the area under the curve? That's just begging a question. Let's use Mathematica in kind of, I think, a fun way. Somebody could send me an email reminding me to put this on Moodle. I'll do so you can play with it if you like. We can program Mathematica to do these approximations for us, and we can program it to do the approximation for large values of n, lots of rectangles. Or if we do trapezoid rule, lots of trapezoids. I can plug in the value of a, like this. I can plug in the value of b, like this. All the semicolons do is just suppress output, but I kind of like putting them between essentially 2 lines of code here. I can, well, let's do it like this. I can type left. Let's do right first. Right as a function of n. I better put my v of t in there as well. V of t as a function of t is t squared. Right is a function of n. I'm about to write a right-hand sum with n rectangles. But wait a minute. How can I do that when I don't know n? I can use the summation symbol. That's how. On the palette, it's right there. Boom, there it is. Summation, capital sigma means summation, add. I need an index of summation. What's that? That's essentially just a letter representing something. typical letter to use here is I. I goes from 1 to n. The convention here with summation notation is that I will first be 1, then it will be 2, then it will be 3, then it will be 4. It gets incremented up by 1 unit each time until you get to I equals n. And whatever formula you write down to the right of the summation, that's the terms that get added. That's kind of confusing. Let's see if we can dispel the confusion. There's going to be a value of the velocity times delta t. I need to add a bunch of areas of a bunch of rectangles. What's delta t? It's b minus a over n. But what goes inside the velocity? That's the hardest part. Do I just put a t? Well, Mathematica doesn't know what the t is. That would be a problem. Whatever I put inside the v has to depend on I, because I is what's changing here. The delta t right there, b minus a over n, is not changing. Whatever n is, that's a fixed number. That's the base of each rectangle. These things are the heights. But yeah, what should go in there? It's a bit tricky. I'll write the answer, then I'll explain it. It's a plus I times b minus a over n. That's kind of complicated. Why does that work? Let's draw a picture to understand why that works. Draw a number line. More notation. So the left endpoint is A. I'm going to also label that t sub 0, the initial value of t. What's the next value of t? Go to the right by delta t units. By next value of t, I mean, say the right endpoint of the first approximating subinterval. And if you're doing a right-hand sum, that'll be the value of t that you plug into the function to determine the height. If that distance is delta t, then this point right there has got to be t sub 0 plus delta t. Right? Just adding delta t to t sub 0 gives me t sub 0 plus delta t. I'm going to call this t sub 1. Go another delta t to the right. What number is that? Let's call it t sub 2. It's t1 plus delta t. But what's t1? T1 is t0 plus delta t. Simplify. This is t0 plus 2 delta t. 2 times delta t. Go to the right another delta t units. What number is that? Call it t3. T3, I've just gone to the right by delta t units, has got to be t2 plus delta t. But t2 is t0 plus 2 delta t. So this simplifies to t0 plus 3 times delta t. You see the pattern? The general partition point, t sub I, if I follow this pattern that I see here, has got to be t sub 0 plus I times delta t. And delta t is b minus a over n. And t sub 0 is a. A plus I times b minus a over n. That's what I was plugging into v in Mathematica. Right there, you can see it. That's what I'm plugging in right there. That's where it comes from. I'm starting I at 1 for a right-hand sum because that's going to use T1 as the first, well, the right-hand endpoint of the first interval to determine the height of the first rectangle. For a left-hand sum, I'd start I at 0 instead of 1 because the left endpoint of the first rectangle is T sub 0. I do want n terms in my sum, so the upper limit of the summation is n. This will work. This will program Mathematica to compute a right-hand sum. Let's also program Mathematica to compute a left-hand sum. I'll copy and paste this after the semicolon. change the word right to left. Start I at 0 instead of 1. I still need n terms, so if that's going to happen, I need an n minus 1 here instead of n. And finally, let's also have Mathematica compute a trapezoid sum by averaging the left and right-hand sums. Got a fraction bar here, left n plus right n over 2. Remember, when you define functions, you need underscores after you define them, including on the right-hand sides of these things. You don't need any underscores. That'll cause problems, in fact. These are functions of n, the number of rectangles, or the number of trapezoids in the last case. So I will enter these. Now they are entered. What can I do with them? I can use them, for example, to confirm the answer as I got before. When n was 5. What answers did I get before? I got a right-hand sum of 440 right there. I got a left-hand sum of 240 right there, and a trapezoid sum of 340. So when I enter this, I should get the numbers 240, 440, and then 340. Yep, there they are. Why did I put them inside curly braces? So that I can get one output, that's why. In what's called a list in Mathematica. It's not a big deal. Don't worry about it. Well, if I can do that for n equals 5, why not do it for bigger values of n? Oh, how about n equals 50? Probably going to give me crazy fractions. Okay, somewhat crazy. There they are. If I put a / capital N at the end like this, it will approximate those numerically to decimal form. And there we have it. A left-hand sum with 50 rectangles giving 323.4, a right-hand sum with 50 rectangles giving 343.4, and a trapezoid sum with 50 trapezoids giving an area of 333.4. Is it right? Well, the left and right-hand sums are not correct. They're different than each other. They can't both be right. The trapezoid sum should be better. Let's go up to 500 rectangles. These numbers are getting closer together. And in fact, if the trapezoid one is the best, it looks like the answer is probably 333.3 repeating meters. What would happen if we let n go to infinity? Limit left n arrow infinity. 1,000 over 3. Yeah, 333.3 repeating. The percent sign refers to the preceding output. / n will do a numerical approximation. I did that with left. Why did I pick left? Oh, because I felt like it. I can also do it with right. I can also do it with trap. The limit is the same no matter what you do. I guess it would have to be if they're all doing better and better at approximating the answer as n gets larger and larger. The limits would have to be the same. Limits. Calculus is all based on limits. There they are. You have to technically define the area under the curve as a limit of areas of approximating rectangles or trapezoids. In general, here's what we write. The definite integral, there we are, beautiful integral sign. The definite integral, wait a minute, it doesn't look like a definite integral yet. It looks like an indefinite integral. Well, that's because I got to put limits of integration, the left endpoint and the right endpoint, below and above. And when I say limits of integration, That's a different meaning of the word limit. I'm not taking a limit. I'm just saying these are on the top and the bottom of the integral sign, limits of integration, or left and right endpoint of your interval, if you prefer, limits of the interval. It's not the same idea as a limit concept in calculus. I write the function that I'm integrating right here, v of t, and just like with antiderivatives with indefinite integrals, I specify what the variable is, t. This notation, especially this v of t dt part, is supposed to remind us of something. It's supposed to remind us of that. V of t times delta t. You know, delta is the Greek version of d. We did use deltas with derivatives as well. Delta is the Greek version of d. V of t times delta t is analogous to v of t. Should I say times dt? Technically, no, but this is another case where calculus has convenient fictions. You could pretend it's v of t times delta times dt. A instantaneous speed times a tiny time interval elapsed. Infinitesimally small. What did I say? An infinitesimally small amount of time elapsed. Wait a minute. What's an infinitesimally small amount of time elapsed? 10 to the negative 10 seconds? 10 to the negative 20 seconds? 10 to the negative 30 seconds? Are those infinitesimally small amounts of time? Well, from a practical engineering perspective, you could say so. But from a mathematical perspective, they're still not small enough. What, 10 to the negative million? 10 to the negative billion? 10 to the negative Google? You kidding me? dt is even smaller than all those by many orders of magnitude. It's smaller than any positive real number, but infinitesimally small. We're talking about the intuitive calculus of infinitesimal numbers here, which don't exist in the real number system. So why are we talking about them? Because it's convenient to do so. They are convenient fictions in the real number system. But if you take a grad school course in something called non-standard analysis, then they become rigorous. Math is wild, wilder than your wildest imaginations. If you go to grad school in math, it's beyond most people's imaginations, including mine when I started grad school. You could actually make this rigorous. Now, Leibniz was the one who coined this notation. He thought of them intuitively. He didn't deal with them rigorously. But he thought of this as a product, rate times time to give a small distance traveled. And he thought of the integral sign as actually being a summation, even though it's not really. It kind of looks like an S. S for some. That's why he made it look this way, because it looks like a fancy S. That's why he made it that way. He was imagining adding up a bunch of infinitesimal distances traveled to get a total distance traveled. All I'm saying here is very hard to understand, yes. But if you keep working at it, you get to the point where it kind of makes sense. And it's super helpful in your science and engineering classes to think of it this way. It gives meaning to integration in so many situations. Makes it a lot less mysterious, even though it's not rigorous math. It's intuitive math. And again, if you think about it a lot, maybe you already have some in Gen Physics. If you think about it a lot, it starts to make some sense, even though I'm not rigorously proving anything. I was a math major and physics minor. I'd sit in my physics classes and they'd do this kind of thing. And I'd say, how do you know you can do that? And they'd say, what are you, a mathematician? And I'd say, I guess so. How do you know you can do that? And they're like, well, come on. It just makes sense. Right? Probably Beacon would say that. It just makes sense. If I asked him to prove it, yeah, he probably wouldn't. Don't assume your science professors can prove it or even want to prove it. Maybe they can, but maybe they can't. But they don't really care, okay? Because it's good enough for them to think about it intuitively. How is this defined, though, a bit more rigorously? It's defined as a limit, if the limit exists, as n goes to infinity of a left-hand sum or right-hand sum or a trapezoid sum. Probably the right-hand sum is the simplest one to write down. Like that. Now, when I say that's a definition, that's a little bit of a lie, a little bit of a fib. It's not really a definition. It's not general enough because I'm only writing down a right-hand sum and I'm not allowing a left-hand sum or a trapezoid sum or maybe some other weird kind of sum, maybe where the delta t's can be different than each other. So it's not really a definition, but it's kind of good enough for us. Where t sub I is a plus I times delta t. But yes, I could change it to a left-hand sum, make I go from 0 to n minus 1. I could average the two. I could represent that as a sum of a bunch of areas of trapezoids. I haven't done that yet, even though I called it the trapezoid sum. I'm writing it as a limit as n, the number of rectangles, goes to infinity. Essentially, that's equivalent to writing it as another limit where the width of each rectangle goes to 0. Those really mean the same thing. You can think about it either way if you assume all the rectangles of the same width. They're all getting skinnier and skinnier. In the limit, if the limit exists, it will equal the area under the curve. In the last few minutes, I think it's worthwhile to mention one other thing here. How do you deal with velocities that can be negative? Oh, let's say like v of t is 4 minus t over the interval from 0 to 10. This is the instantaneous velocity at time t, say in meters per second. Could I still do approximating rectangles, still compute a limit, and still do an integral? Yes, you can. Does it give the distance traveled? No, it doesn't. In this case, the integral, well, let's go from 0 to 10 here, of this function, which I'll write here, 4 minus t, which, yes, could be written as a limit of approximating rectangles, is no longer the area under the curve, and it's no longer the distance traveled. But it still can be interpreted in terms of areas, and it's still related to distance, you could say. Instead of the distance traveled, it's the change in position. Change in position. And instead of the area under the curve, it's the area between the curve and the horizontal axis, where areas above the t-axis count positively and areas below the t-axis count negatively. What does that mean? Well, what does the graph look like here? Looks like that. I did make this example linear. The velocity at time 0 is 4 meters per second. So at time 0, you're traveling to the right by 4 meters per second. But by the end, time 10, you're traveling to the left at 6 meters per second. The negative sign means you're traveling to the left. What's the average of those two numbers? Average is 4 plus negative 6 over 2. is -1 meter per second. Over 10 seconds, what's your change in position? -1 meters per second times 10 seconds is -10 meters. What does this mean? It means you end to the left of where you started. If rightward is positive, leftward is negative, you travel to the right a bit, then you turn around, you go to the left, and you end further to the left of where you started, 10 meters to the left of where you started. And it is this area, call this A1, minus this area, call this A2. You can check, those are both triangles there. This is A1 minus A2. I would encourage you to do that sometime in the next 20 minutes to confirm that you can see that. Compute the areas of those triangles and do the subtraction. You should get -10. Okay, you could do it right now. It should take you 30 seconds.